Hello and welcome back. In this video, we are going to step away from solving rational equations and instead talk about solving rational inequalities. Now, with solving rational inequalities, it's actually going to be extremely similar to solving polynomial inequalities, quadratic inequalities, and so on and so on. We're going to be utilizing factoring a lot as well as a number line and a sign table. So if you've already covered solving polynomial inequalities, this is then going to look extremely similar. There's just one extra piece or maybe a couple pieces of information that we must cover. So let's jump right into a problem. For example, this problem here, we have a typical rational inequality here. Now, there are going to be quite a few steps to solving rational inequalities, and sometimes you're able to skip one or two depending on what you're given. And in this particular problem, we're actually going to be able to skip what is known as the first step, which is to move everything onto one side of the inequality. Basically, we want everything on one side of the inequality and zero on the other side. The reason for this is because it allows us to use a sign table to test if the values are either positive or negative. Because if we want to be less than zero, we want negative values, we want negative numbers, we want negative answers. And if we want to be greater than zero, we want the exact opposite. We want positive answers. So as you can see, we actually already have everything on one side of the inequality, so we're actually able to skip this step and move on to step 2, which is to write that as a single factored fraction. Now, notice I underlined single. That's because in some cases, when we have to move pieces around from one side to the other, we're going to have to use those adding and subtracting skills that we have picked up to combine those to a single fraction. Now, this one's already a single fraction, but it is not factored, so we need to make sure we go ahead and factor it as such. Now, from there, we need to identify the zeros of the numerator and the denominator. So I'm basically going to set every single factor in a numerator and denominator that has a variable in it equal to 0 and solve for x. So that would end up getting us x can be 2 or negative 2 from our numerator, and x can be negative 3 and 1 from our denominator. Now, I'm going to give you a slight warning here. We're going to cover this when we get to the sign table as well. Remember, our denominator cannot be 0. So even though we're finding zeros of our denominator, we're going to have to exclude those from our final answer since we technically cannot be those particular zeros. But what they're allowing us to do is to set up our number line, and all of these zeros of the numerator and denominator are going to be key features of the overall graph, which is overall what this is helping us identify. From there, we're going to set up our number line with those particular zeros. So I set up my number line. I have zeros of negative 3, negative 2, 1, and 2. So I just go ahead and I place those on a number line. And now we got to think about if we're going to shade those points in with a solid circle or use an open circle. And that really depends on the problem as well as the zeros placed in the numerator or denominator. Now, in this particular problem, it is less than or equal to 0. Remember, when it's or equal to, we can use solid circles. We can be particular values. The only thing is, we still cannot actually be 0 in our denominator because that means we'd be dividing by 0. Now, if this was strictly less than 0 or strictly greater than 0, everything would be open because we couldn't be 0 to begin with. But because of the or equal to, this kind of presents us in a little bit of a situation here where we have to identify that, hey, we can be negative 2 and positive 2 because those are values that make our numerator equal to 0, which is okay because it's or equal to 0. So our numerator can be 0. However, our denominator still cannot be 0. So I'm going to leave negative 3 and 1 open, which is excluding those values because I still cannot have a 0 in my denominator, okay? And then I go ahead and set up the sign table. This should look kind of familiar to you if you've covered polynomial inequalities with such. From there, we actually go ahead and we test values in each interval. That's what the sign table is going to help us do. It's going to help us stay organized. But we're going to test values in each interval to determine if that interval produces a positive or negative value. Because if I want to be, in this particular example, less than or equal to 0, I am actually going to want to be the negative values. But I'll get to that in just a moment. So I go ahead and I'm going to start testing out any numbers in each interval. So I needed to test some number less than negative 3. Why not negative 10? When I plug in negative 10 for x, negative 10 plus 2 is negative, negative 10 minus 2 is negative, negative 10 plus 3 is negative, and negative 10 minus 1 is negative. And notice we end up with 4 negatives. So we have a negative times a negative in our numerator, which would be a positive, and then we end up with a negative times a negative in our denominator, which would end up giving us, once again, a positive, which would then evaluate to a full positive. Kind of a cheat. Not a cheat, just kind of a little trick, I guess you can use, is that if you end up with an even number of negatives, those are going to multiply and cancel out to get you a positive. If you end up with an odd number of negatives, then they won't all multiply and cancel out. You're going to be left with an odd negative, which makes the entire interval negative. That's something that might make it a little bit easier and allow you to solve these a little bit quicker. From there, I test out some number in between negative 3 and negative 2, like negative 2.5, and that interval ends up becoming negative. I test now some number in between negative 2 and 1, and I just pick 0. And remember, I'm just plugging these numbers in for x. 0 plus 2 is positive. 0 minus 2 is negative. 0 plus 3 is positive. 0 minus 1 is negative. All of that together ends up making a positive interval. And I just keep doing this. I test numbers in between 1 and 2, say 1.5. That produces 3 positive intervals and 1 negative, which produces an overall negative interval. And then I test out some value larger than 2, say like 10, and it just makes everything positive, so we stay positive. And then you're pretty much done. From there, we have to state what our solution is in the specified format. Does your teacher want it in interval notation? I do. Does your teacher just want it shaded on the graph or just written in inequality or set builder notation? We're going to be focusing on interval notation, but I'm actually going to shade the graph as well, or the number line, shade the number line as well, just to make it a little bit more visual. Now, since I want it to be less than or equal to 0, we are going to want the negative intervals. If we were greater than or equal to 0, it would be the exact opposite. And that's why we actually want everything on one side of the inequality and 0 on the other. It's very easy, and it's to test if an interval becomes positive or negative. As opposed to, let's say we are less than or equal to 1, there's a lot of different combinations that can produce a value that's greater than 1 or less than negative 1. It's a lot harder to test that. It's a lot easier to just compare to 0, because then we're just comparing if it's positive or negative. Now, in this case, we want negative, so I have 2 negative intervals. So notice, if I want, I can shade those in, and this would be a visual representation of where our solutions lie. It would be, all the solutions would lie between negative 3 and negative 2, as well as in between 1 and 2. And some of those would actually be included. So our final answer would be from negative 3 to negative 2. Notice I'm including negative 2, so I put a bracket on negative 2, parenthesis on negative 3, because I cannot be negative 3. Or, remember U for union, or from 1 to 2, notice I cannot be 1, so I put a parenthesis on 1. I can be 2, so I put a bracket on 2. And that would be our final answer. Now, these ones require a lot of work, and they do take a little bit of practice to get used to them. But once you got them down, these really aren't too bad. So I want to take a look at just a couple of more examples. The next one's going to be very similar to this, where we don't have to move anything. It's already a single fraction on one side. And then the very next example, we are going to actually have to move a fraction from one side to the other. So let's take a look at our second example. All right, so here is our second example. So notice we already have everything on one side of the inequality. I don't need to move anything over. Remember, your first step is to always have everything on one side of the inequality, 0 on the other. And from there, we want to make sure that everything is in one factored fraction. So if you have multiple fractions, if you have multiple rational expressions, use your skills with adding and subtracting rational expressions to combine those into a single fraction. If you already have that, or once you have that, then you just need to go ahead and factor completely. So that's what I went ahead and did. We factored the numerator, we factored the denominator, and from there, we want to state what all the zeros of the numerator and denominator would end up being. So basically, set every factor with a variable in it in both the numerator and denominator equal to 0 and solve. And there we go. We get 1/2, -3, 5, and -5. From there, we're going to want to set up our number line as well as the sign table. So notice I'm setting out my number line. I plot all my zeros on there. -5, -3, 1/2, and 5. And now we got to think about if it's going to be solid or open. Now, this is greater than or equal to 0. That or equal to gives us the possibility of actually being 0. Now, if it was strictly greater than or strictly less than, everything would be open. All these zeros would be excluded. But because it's or equal to, I'm going to have to include at least some of the zeros. And the ones we always include if it's or equal to are the zeros that come from the numerator. Because I can't have a 0 in my numerator, I cannot have a 0 in my denominator. So notice I'm including 1/2 and I'm including -3 because those are coming from our numerator, and I'm excluding 5 and -5 because those come from our denominator. You can see as the open and closed circle whether it's included or excluded, and then we go ahead and we set up our sign table. And from there, we're just going to go ahead and test each interval. So I need to test some value less than -5. I chose -10. When I plug in -10 for x in each of these 4 factors, all 4 of them are negative, which turns that entire interval into a positive. From there, I tested some number in between -5 and -3. -4 seemed like the obvious choice. When I plug -4 in for x in all 4 of these factors, 3 of them ended up becoming negative. Only 1 of them was positive, which means the overall interval is negative because there was 3 negatives, an odd number of negatives, that's going to stay negative. From there, I had to test some value in between -3 and 1/2. I chose 0. If I can use 0, I'm always going to use it, and that produced a positive interval when I plugged in 0 for x. Then I had to test some number in between 1/2 and 5. I chose 2. You could have chose 3 or 4 as well, or even 1. I chose 2. That once again produced 3 positives but 1 negative, which made a negative interval. And then I need to test some value larger than 5 for the interval greater than 5. I chose a number 10. It makes everything positive, which means the overall interval is positive. From there, I have to determine if I want the positive or negative intervals. And that all stems from whether or not we're greater than or less than or equal to. Since we're greater than in this particular case, more specifically greater than or equal to, we want the positive intervals. It didn't matter if it was greater than or equal to or just greater than. If we're greater than, we want to be positive, okay? So what that means is that all 3 of those intervals that ended up becoming positive are going to be part of our final answer. So as we can see, we have 3 separate intervals, one of which is from -infinity to -5, from -infinity up to -5. Both are excluded. Remember, you can never be in infinity. Our next interval is all the values in between -3 and positive 1/2. And notice those are included, so those get brackets. And then from there, it's all the values greater than 5, so from 5 to infinity, okay? And those are both excluded. And that would be our final answer, okay? So I covered those particular problems because they're a little bit more straightforward because I didn't have to move anything over, but I wanted to introduce the greater than or less than or equal to, because the or equal to is what trips some people up. Now I want to take a look at a problem where we don't have everything on one side of the inequality and we don't have a single fraction. So let's go on and take a look at that problem now. Okay, so as we can see in this problem, I don't have everything on one side of the inequality and 0 on the other. I'm going to have to move one of these fractions to the other side in order to have this written as a single fraction. So I chose to subtract each side by 1 over x plus 4 to move that fraction over to the left side of the inequality. And now notice I have everything on the left side of the inequality, 0 on the other side, but I do not have it written as a single fraction. So that's what I'm going to have to do. I'm going to have to get a least common denominator and use my skills of adding and subtracting fractions to get this written as a single fraction, and then simplify and factor as much as I possibly can. If you have already covered adding and subtracting rational expressions, this shouldn't confuse you at all. If you haven't, or you haven't mastered that, make sure that you go back and rewatch those videos, okay? It's an extremely important skill, especially for these types of problems. But from here, I have everything written as a single fraction. Notice I have this completely factored, so I have 4 times the quantity of x plus 6 in my numerator, and I have the quantity of x plus 4 times the quantity of x minus 4 in my denominator, and that needs to be greater than 0. So now I find my zeros of the numerator and denominator. I get -6 from the numerator. I get -4 and +4 from my denominator. And then I set up my number line. I only got 3 zeros in this particular case, so that's totally fine. We set it up the exact same way. And now because this one is not or equal to, I don't even have to worry about what should be open, what should be closed, what should be included, what should be excluded. Since it's not or equal to, all of them are excluded. All of the values are going to be open. And now I can go ahead and set up my sign table. And notice 4 is a factor, so technically 4 should be in the sign table. Now, if you don't want to have that 4 in the sign table, you technically could actually divide each side of the inequality by 4 and get away with it. The only thing that I want you to be aware of, though, is if you divide each side by a negative number, remember that means you must actually flip the inequality symbol. So just be really careful when you're doing that, okay? Otherwise, I'm just going to leave that 4 there, and I'm just going to have a factor of 4, and that shouldn't really change much because 4 is always positive, right? It doesn't matter what I plug in for x, there is no x on that 4. It's just 4, and 4 is always positive. So across the board, that is going to be positive. Now for the rest, I need to go ahead and actually plug in a value of x in each interval. So I plugged in values of -10, -5, 0, and 10, and this is what my sign table ended up producing. Now, from here, we want to know what our final answer should be. Well, we want to be greater than 0. Right? So that means we want to be positive. Well, if we want the positive intervals, we should shade all those positive intervals. So our answers are going to be all the numbers in between -6 and -4, both are excluded, and all the values strictly greater than 4, with 4 excluded. So we have 2 intervals, so our final answer is going to be 2 intervals. And there we go. -6 and -4, parentheses around both because we cannot be -6 or -4, and from 4 to infinity, with obviously both of those excluded because we can't be in infinity, and we also can't include 4 because it was not or equal to, as well as 4 came from our denominator. And that's it. That's solving rational inequalities. We're not going to go too much more complicated than that. Really, as long as you're able to factor, as long as you're able to add and subtract rational expressions, and if you can set up a sign table and use it correctly, you should be able to do these. I hope this video was helpful. If there's any questions, please feel free to reach out and let me know. Otherwise, I look forward to seeing you guys in the next video.